Hello, welcome to episode 2 in the series on Big O notation. I'm Max and I'll be your host for this episode. Last episode we talked about and entered the world of why we use Big O, which is a way to describe how many steps in an algorithm are needed as the input size increases. In this episode we'll be discussing these major quadratic time algorithms: bubble sort, insertion sort, and selection sort. The best, worst, and average case for bubble sort, order n squared, order n, and order n squared for average again. For insertion, it's order n squared, order n, and average is order n squared, just same as bubble. For selection, however, it has the same worst, best, and average case, which is order n squared. Now you may notice that the average, worst case, and best case scenario are very similar between these different sorting algorithms, except their best case scenarios, with bubble sort and insertion sort having to take less steps in their best case. So now that you know that, let's start with bubble sort. So imagine we have a line of numbers which is 12, 8, 7, 9, and 2. So now what you're going to do is you're going to go down the line, comparing each number with the one next to it, 2 at a time. If they're out of order, meaning that the one to the left is bigger, swap the two. For example, 12 and 8 right here would swap with each other to become 8 and 12. So it would go to like 8 and 12 would swap. 7 and 9 would swap. Or no, it's instant. Let's try like this. Okay, now we have that. So we're gonna like bubble the largest number through the list like this. So 7 and 12 swap now, so it would turn into 8, 7, 12, 9, and 2. 7 and 8 and 9 and 12 swap again. So 7, 8, 9, 12, and 2. And 12 is bigger than 2, so those would swap. So it would be 7, 8, 9, 2, 12. And then 2 would just keep swapping down to the end of the list, and it would turn out sorted like this. Alright, it may be simple and easy to visualize. It's pretty easy to do. But with longer lists, like 1,000 numbers or even like 50 numbers, it would take so long. So now try to do it on your own with, let's do 8, 7, 2, 9, and 0. Do it on like a piece of scratch paper, whatever you have. Out of 3, it has the best case along with insertion sort of order n, which means if the list is 5 numbers, its best case would take 5 steps. In what scenario would you think this best case scenario would happen? The answer is if the list was already sorted. Now you might want to see some bubble sort in C#. I'll explain the code. Alright, here we have it. It's decently long. So this first part is actually declaring the array, what numbers you can use. So like 64, 34, 25, 12, 22, 11, and 90. Alright, it creates an array of integers that you want to sort in ascending order, so got that. Now, this line isn't necessary really, but it, before the sorting, it prints the original array so you can see what it looks like before all the sorting. So this calls the sorting function, which actually performs the sorting step by step. This part right here. Okay, so this is actually inside the function up here. N stores the length of the array, so got that. Swapped here, this swapped is a flag that checks if any numbers were swapped during a pass. If no swaps occur in a full pass, that means the array is already sorted and the algorithm can stop early. This part right here. If no swaps happened in a pass, the array has to already be sorted, so the algorithm stops early, using this break function. Makes it more efficient and, yeah, fast, I guess. Now we're moving on to insertion sort. So insertion sort works like sorting playing cards in your hands. It works by iteratively inserting each element of an unsorted list into the sorted portion of a list. So, say we have, what is this? Okay. Erase all that. Alright. So let's say we had a list of 11, 12, 13, 15, 17, 14, let's do 5, 3, and 2. So look at each number one by one, adding them to a new list that has them in the right order. So we see first 11, 12, so 11, 12, then we look at 13, so it's in front of 12, so 13 here. Wait, if I erase this part, oops. Alright, yeah, so then 13, then we see 15, then we see 17, all this is in order so far, then we see 14, which is in order, so we add it right here, right in front of the 15, that's very clear. Give it some space, be right here. 14 be right in front of 15 between the 13. Now we have 5, which is all the way in front. Then we have 3. And finally we have 2. So insertion sort is very efficient at smaller lists and almost sorted lists. In the best case, it's order n, meaning you have to look at every number in the list, and its worst case is order n squared, meaning you have to look at each number in the list squared. The list is completely out of order. Now you might want to see some insertion sort code in C# too. Let's get it pulled up. Alright, so again, this part is declaring the array of your numbers 12, 11, 13, 5, and 6. It creates an array of integers, yeah, pretty much. So this part prints the original array again. Not necessary, that's my opinion, I don't think it is. This part is, this runs the sorting function to actually organize the array in ascending order. Let's see, where are we? Oh, here we go. Wait, no, oops, it's right here. Yeah, alright, here we go. Once all larger elements have been shifted, the key is placed into its correct position. That's what this is doing. and then this right here. This is an optional line which prints how the array looks after each insertion step, which just helps again visualizing everything. And then this right here, after the loop finishes and the array is completely sorted and all, that's fully displayed right here. Alright, yep, that's it for the insertion sort C# code. Now we're moving on to... Now we selection sort. Alright, let's erase all this first. Alright, it's a comparison-based sorting algorithm, and it sorts an array by repeatedly selecting the smallest element from an array and swapping it with the first unsorted element. This continues until it's finally sorted. So let's say we have, let's do 12, 4, 7, 98. Oh, what's a weird date? Hold on. 98, 5, and 2. It would look, yeah, so it would kind of look like this. So this would swap all the way down here, so it'd be 2, 12, 2, 12, 4, 7, 98, and 5. Now we would swap 4 here. Yeah, we would, do 2, 4, 12, 7, 98, and 5. Then you see 5, so you do 2, 4, 5, 12, 7, and 98. And then you'd swap 7 in there, 2, 4, 5, 7, 12, and 98 sorted. This is actually the worst one in the list, at least I think it is. It will always take order n squared. I mean, it's consistent, but its time isn't the best, and that's just will take. Yeah, it's worst case, best case, average case are the same. Even if it's already sorted, it'll still take the same amount of time. As you can see right here. Let's see selection sort in C# real quick. Alright, so again, we're declaring an array, see the numbers, all this right here. Now we're gonna print the original array right here, so we can see everything. This right here, min index starts at the current position I, assuming that that's the smallest number. Then the inner loop goes through the rest of the unsorted portion of the array to find the smaller value. If it finds one, it updates min index from where the smallest number is. This right here, once the smallest number in the unsorted section is found, it swaps places with the first unsorted element. This means that by the end of each pass, the smallest remaining number is locked into its correct position. Alright, so this, after every pass, the program prints out the current state of the array so you can visually see the progress of the sort. And then our final output is printed here. So, now you know all about these 3 algorithms and their different strengths. Bubble sort is simple and good with smaller lists, but it gets slower as more numbers are added. Insertion sort is good for smaller or nearly sorted lists, but again, it gets slower as more numbers are added. And selection sort, it's consistent, having the same worst, best, and best case and average case. But it's kind of takes a lot of steps. Order n squared always instead of just order n. Alright, that concludes our lesson for today. We hope that you enjoyed and see you in the next episode, Fast and Structured, which will introduce you to 2 more sorting algorithms. Merge sort and heap sort. See ya.